Hi, it's a discussion of the Notes 20 for Math 521. This will be the last lecture. I am going to have some additional notes, number 21, on discontinuous Galerkin methods. But that's a very technical discussion with pretty detailed notes based on a research article that you can look up. So I'm not going to give any commentary on those. But today's subject is error estimation for finite element methods for elliptic problems. and I thought a little bit of warm up would help you work through those. Again, there's detailed notes that are posted, and the discussion is also based on a particular research article, which is listed in the notes, so you can see even more details. But I'm going to give you some, like I say, some warm up of how it goes. Okay, let's have a start. We have a elliptic problem, and I'm going to start with our usual 1D periodic boundary value problem as an example. And we have a finite element approximation of that problem, and we want to know how accurate it is, so we can figure out if it's accurate enough for the application that we're interested in. As a follow-up discussion, which well, I'm not going to follow up on in Math 521, but an interesting question is, if it's not accurate enough, then you need to refine the grid somewhere, but maybe not everywhere. And so what you'd like is to not only have an indication of how accurate your approximation is, but where the accuracy is limited locally by the grid level. And then you can refine the grid in those areas to get an approximation without having to refine the grid everywhere. Now, if you look at the article that's listed in the notes, they have some progress on that kind of local question. But I'm going to say this whole game of error estimation for finite element methods, this is not a finished story. Not like it is for time-stepping methods where people really know what to do and how to get it to work well. There are many more open questions in this error estimation for finite element spatial approximations that you could go on to as a research career if you were interested. Okay, so let's make things concrete. I have our usual problem, and I'm going to compute a finite element approximation, which I'm calling U1. 1 because it's a first order approximation using what we started with right at the beginning of the term, piecewise linear elements on n subintervals. And the question is, how accurate is this approximation to the exact solution? Now we're going to start borrowing some ideas from error estimation and time stepping. And if you remember, there were two ways to go about estimating local errors for time stepping. One was find an alternate time step, preferably one that's cheap to compute, that has the same dominant error term as the scheme that you're using. And then you can use the difference between the two computed things to estimate the dominant error, and then control the time step so that's below a tolerance. The other one was to use a higher order method as a more accurate approximation of the solution, and then comparing your approximation to the more accurate approximation also gives you an estimate of the error. And that's where we're going to start with the finite element setting. So I'm going to consider computing an approximation that's finite element on the same grid that's a higher order accurate approximation. And remember, right somewhere in the first few weeks, we talked about piecewise quadratic elements in 1D and also in higher dimensions. And so, well, you know what's coming. I can compare my low order approximation to the high order approximation to get a good estimate of the error. And here's the simple triangle inequality that shows that. And so if you look down here, you can see comparing the first order approximation to the second order approximation on the same grid, although this has twice as many unknowns as this one, right? This gives an asymptotically accurate estimate of the error in the low order approximation. But remember what worked for time stepping, that the high order thing that you are computing, or the other thing you're computing, if it's the same order, has to be cheap to compute. And for time stepping, that was using a explicit just one step of an explicit method to use to compare to an implicit time stepping method. And the explicit time step is cheap to compute. And then the other one was this RK45, where there was only 50% more work, roughly, because the fourth and fifth order methods shared stages. Here, this is not true, right? It's twice as big a problem to compute this high order method. And in fact, the bandwidth of the banded matrix for a direct solve is bigger, so it's actually more than twice as much work. And of course, if you looked at higher order elements in higher dimensions, there's significantly more work computing U2 than U1, and so this doesn't make any sense. And so there's a little game that you can play. Okay, so let's have a look and see how that game goes. So let's think back to the space of functions that U1 is in. They're the space of piecewise linear functions on subintervals, continuous functions on subintervals. And there's a basis for that space of functions. This is the first basis set that we saw, these hat functions. And then if I look at the quadratic, piecewise quadratic space of functions, this is going back to the beginning of the term, but there were two types of basis functions. There were these ones that spanned two subintervals, right? And there were interpolation points at the end of the subintervals and at subinterval centers. And then there were these bubble functions, which just lived on one subinterval. And of course, the convenient thing about this choice of basis function is the basis coefficients are equal to the values of the function at these points, subinterval ends and centers. But if you're willing to give that up, a perfectly good basis for Qn is these piecewise linear functions. These are the ones that we started with, okay? And just add in these guys. You know you need two n basis functions for Qn, but instead of using n of these and n of these, I'm going to use n of these and n of these. And the span is the same. So I should have had the Sn is the span of these, and Tn is the span of these. It's the same space Qn. So Qn is equal to Sn. Well, I should put plus with a circle around a Tn. So linear combinations of Sn and Tn. So there's a little bit of a mix-up in the notation here in the notes. I hope you will forgive me. It's too late not to forgive me, I guess. And in this basis, remember for our basic problem, the matrix that we compute is just the stiffness matrix plus the mass matrix. Okay, and in this basis, if I list all of these ones out and then all of these ones, well, I just get the integrals of the basis functions from Sn with themselves in this block. I'm writing out this matrix, which is 2n by 2n in terms of n by n blocks. Okay, and this one is just the k plus m for the original low degree polynomial approximation. Okay, and then of course over in this block, I just get the integrals of the psi i's with themselves. So here's the stiffness plus mass matrix entries. And you notice this matrix T, because these guys don't interact with each other, right? They're all on separate subintervals. This turns out to be a diagonal matrix. And then, of course, there's off-diagonal terms, right, which look like this. And there's a B and a B transpose, and I may have got those mixed up depending on whether you call I the row or J the row. Okay, so B or B transpose in one of these places. It's a symmetric matrix. As you know, it's going to turn out to be. Oh, whoop. Okay, so now let's look at what U2 solves. Well, it solves a weak formulation restricted to the subspace. So again, this shouldn't be union. This should be a direct sum. So linear combinations of this plus linear combinations of this. So this solves the usual problem. I have to take the inner product of this approximation with any test function in this space. So that means any test function in these spaces. You notice, of course, if I solve for U2, then the coefficients of the original basis vectors change from the solution U1, right, which is also a linear combination of those basis vectors. But U2 would change those and then add some extra coefficients of this new basis set. So here is the tricky idea. So instead of solving for U2, this is the higher order accurate approximation, I'm just going to compute a kind of partial correction, right? This makes U2 have the right inner product with every V in the whole space. If I just looked at U1, U1 would have this property for every V in Sn. So let's just add something which is only in this space and make the thing that I add in the additional degrees of freedom orthogonal to those additional degrees of freedom. Now, right, that's like crossing out these terms here, which of course would change the solution in the original subspace. That's what I was talking about before. But I'm just going to say, let's look at a sort of a partial fix. Right, so I can solve this problem, and of course that is just the same as crossing out these off-diagonal terms and moving all of this stuff over to the right-hand side, okay, and I will only have a diagonal system to solve. Okay, so this is not a pi, this is the matrix T, it's a diagonal matrix, and I have some right-hand sides, which are these things which you can work out from the previous slide. And of course this is fast, right? This is just a diagonal matrix. Now, if you look at the same story in higher dimensions, then this matrix, this block, won't be a diagonal matrix anymore. But now we're getting into some gritty details. If you look at the paper that's referred to in the notes, they show how you can use a diagonal approximation and still have the property that I'm going to show below. So this is shown explicitly in the notes in this 1D setting, that this W, which is not the same thing as U1 minus U2, it's just some sort of partial, some sort of reduced dimensional version of it, but it's still an accurate estimate of the error in U1, in that you can show these precise bounds, right? That if you look at the error in the solution, W is less than that. More importantly, it's bigger than some non-zero constant times the error. And so what is this constant? Well, okay, you want to make sure that both of these two terms are bounded away from 0, which means gamma and beta should be less than 1. The gamma less than 1, that is that these two subspaces in the natural norm of the problem, which in this case is H1, right, are not asymptotically parallel. So they're not perpendicular, which would, if they were perpendicular, then these blocks would be 0, okay? But you can show that they don't, that they always have some non-zero angle between them. And in the notes, there's an explicit calculation that shows that's true in that 1D setting, okay? The beta less than 1, that goes back to this idea that the higher order approximation is more accurate than the lower order approximation. So this is something you know is true for H sufficiently small, right? Okay, so that should put in perspective the more detailed notes. And then if you are really interested, you can follow up with the paper that's referred to in the literature. Again, I want to say error estimation for finite element methods in many different situations is still a ongoing research topic. So I don't want you to think that this is, the only way to approach these problems, or that this is somehow better than some of the other things that you might see in the literature. But it was, I thought, an accessible, well-written article. So it's a nice thing to start with. Okay. Enjoy the notes, and this is my last, I guess, online time. So I'll say it's been a pleasure to have you in the class, and well, okay, and for the last weeks, not in the class, but interacting by email. And I wish you all the best for the end of term, through the summer, and in particular, however long it takes life to get back to normal, wherever you call home. Good luck.